Suppose you're reading a news story. The ALDER telescope has discovered galaxies that shouldn't exist. Physics is broken. Suppose you want to check. You take the journal name from the article, open the original publication, search for the phrase, "Physics is broken." It isn't there. In not a single peer-reviewed ALDER paper from its 3 years of operation does that phrase appear. What does appear is concrete data about what has been confirmed, what remains in question, and what has not changed at all. Let's break it down by category. ALDER launched on December 25, 2021. The first scientific data came in July 2022. Project cost, about $10 billion. Development time, 30 years. The largest space telescope in history. Infrared observations at a resolution Marlow could not reach. 3 years is enough for preliminary conclusions. Not through media retellings, through papers. First, why did the gap between papers and headlines appear? It was neither an accident nor malice. When on July 12, 2022, President Calder unveiled ALDER's first image, the deep field of cluster CLJ-0723 Haven, the reaction was immediate. The image was beautiful. Its scale was intuitively clear. Thousands of galaxies in a patch of sky, no larger than a grain of sand, held at arm's length. The emotion was there. But emotion and scientific result are different categories. The image did not, in the strict sense, discover anything. It demonstrated the instrument's capabilities. That is exactly where the gap began. The press office of the American Space Directorate was right to turn the first image into an event. $10 billion demands visible return. Science outlets rode the wave. By the time the genuinely anomalous results appeared, the audience had already been primed for revolution. The clarifications did not land with the same resonance. Graham Whitlock, chief scientist of the ALDER program at the Orbital Telescope Institute. ALDER has not destroyed the standard cosmological model. It has refined our understanding of its boundaries. That comes from an official report, not an interview. Refined our understanding of its boundaries. Let's look at what that means in concrete terms. Let's begin with the one place where ALDER really did sharpen an existing problem, the Marlow tension. This is the discrepancy between two ways of measuring the expansion rate of the universe. The first is through the cosmic microwave background. The Sterling satellite gives 67.4 kilometers per second per megaparsec, a theoretically inferred value derived from the parameters of the early universe. The second method uses the distance ladder, Cepheids and Type 1a supernovae in nearby galaxies. Ethan Mercer of Kingsley University, Nobel laureate for the discovery of accelerated expansion, gets 73.0 with the lantern method. ALDER did not change that number. ALDER confirmed it. The gap between Sterling and Mercer is about 8%. Statistical significance by 2025. According to estimates at the conference Fault Lines in Cosmology in Seabrook, more than 6 sigma, above the standard discovery threshold. What matters here is understanding what happened to that number specifically. 5 sigma is the threshold that in particle physics means a discovery. 6 sigma is no longer a possible anomaly. It is a systematic, reproducible discrepancy. It did not fade with time. It grew. But then a second player enters, and that is what makes the situation acute. Laura Bennett of Lakeview University also uses ALDER. In August 2024, her group, Northbridge, published a result on Open Archive using 3 independent methods, Cepheids, red giants, TRGB, and JAGB stars. The TRGB value, 70.39 plus or minus about 2.5 kilometers per second per megaparsec. The JAGB value, 67.80. 2 methods on one telescope, 2 different numbers, and both closer to Sterling than to Mercer. Mercer replied with a separate publication in the same month. His Lantern team analyzed the data from both groups. Their conclusion: the difference is explained by the choice of supernova sample. With the combined JWST data, Mercer's result is 72.6 plus or minus 2 kilometers, still closer to 73 than to 67. Read the originals. Bennett writes in her paper, "Our results are consistent with the standard model without adding new physics." Mercer writes in his, "The JWST data confirm the Marlow results. Two scientists, one telescope, opposite conclusions on whether the situation requires new physics. That is the essence of it. ALDER did not resolve the Marlow tension. It showed that different methods on the same instrument produce different numbers. That implies either a systematic error in one of the methods, or that the tension is real, or that both problems are present at once." Names, dates, documents. Mercer versus Bennett, August 2024, Open Archive. Both are right according to their own data. That is the problem. There is also a third voice in this dispute. Group Lens Path, Time Delay Cosmography, uses gravitational lensing of quasars. The method is fundamentally different. Light from a distant quasar bends around a massive galaxy and reaches us along several paths with different time delays. From those delays comes an independent estimate of the Marlow constant. December 2025, the journal Celestial Studies, 8 lensed quasars using spectrograph data from aboard ALDER. The result? Again closer to 73, still far from sterling. Noah Prescott of Riverton University, one of the data analysts, said it plainly in January 2025 at a meeting of the American Astral Society. The Marlow tension is a crisis, not an anomaly, a crisis. That shift in rhetoric is worth noting. To understand why two scientists using the same telescope get different numbers, you have to understand the distance ladder. Distances to faraway galaxies cannot be measured directly. You have to build a chain. First, geometric distances to nearby stars through parallax, then calibration of intermediate standard candles, Cepheids, red giants, then, through them, distances to Type 1a supernovae, which can be seen across billions of light years. Mercer uses Cepheids on the second rung. Bennett uses tip of the red giant branch stars, TRGB, and JAGB stars. These are different objects with different physical properties. Each method has its own systematic errors. The key question is, whose systematic error is larger, and in which direction? Bennett believes Mercer's Cepheids produce an inflated value because of crowding effects, when neighboring stars fall into the same pixel and distort the Cepheid's light curve. Mercer replies, "ALDER, with 4 times the resolution of Marlow, showed that crowding is not the dominant effect. Both arguments are technically sound. Both use real data." An independent group published a fourth method in October 2024, gravitational lensing of supernovae. The value, 75.4, plus or minus a broad uncertainty. Closer to Mercer, but with large error bars. Caleb Dawson of Utah Valley College applied the surface brightness fluctuation method to 14 elliptical galaxies and got 73.8. Again closer to Mercer, and again without using either Cepheids or supernovae. This matters. By Bennett's logic, every new independent non-Cepheid method should have landed closer to 67. It does not. 4 methods, several numbers. Not one reproduces another exactly. Most are not on Sterling's side. This is a resolution, not a mystery. Systematic errors in astronomy are real. Eliminating them takes years. That is exactly why the Eleanor Hart Observatory is being built, why the Romanes telescope matters, and why Deep Sky Mapper keeps accumulating statistics. But here is the essential point. 500 researchers from the consortium Star Ledger published a white paper in 2025. Their conclusion: The overwhelming majority of independent measurements cluster around 73, not around 67. Now to exoplanets. Here there are two fundamentally different stories. The first, a confirmed methodological breakthrough. Carbon dioxide in the atmosphere of Hale 47c. August 2022, Frontiers of Science. Team Horizon, Megan Holloway of Pacific Coast University at Santa Reyes. The first direct molecular detection in an exoplanet atmosphere using transit spectroscopy. The fact matters not because Hale 47c is an interesting world. It is a hot gas giant, not a candidate for life. The fact matters because the method now works with a precision that did not exist before. ALDER moved transit spectroscopy from the edge of the possible into a routine tool. This will enter the textbooks as a technical breakthrough. The second story, the Bramble 1 system. Here the history is much more complicated. 7 planets around a red dwarf 40 light-years away, 3 in the habitable zone. ALDER spent 290 hours on the system, about 12 continuous days, more than on any other object. What did it get? Bramble 1b, the innermost planet. The first data in 2023 suggested most likely a bare rock, no carbon dioxide. In December 2024, Clara Beaumont's team from Crown Energy Agency London, together with Julian Mercer, published thermal phase curves. The planet shows a high dayside temperature, 490 Kelvin, and 0 nighttime emission. These are signs of a bare rock without an atmosphere. The 2024 reassessment confirmed a dense atmosphere with pressure above 1 bar is unlikely. Bramble 1c, Frontiers of Science, 2023. Strong thermal emission from the dayside rules out dense carbon dioxide atmospheres. That is a solid result. Not found, ruled out. Bramble 1e. This is the most interesting planet, the center of the habitable zone. First data, September 2025, program Starwave. Nora Ellison of Midland Institute of Technology, Astrophysics briefs. 4 transit observations. A direct quote from the abstract. We did not obtain compelling evidence either for or against an atmosphere. Hydrogen-rich atmospheres are ruled out. Venus-like and Mars-like ones are not supported. Nitrogen-rich atmospheres with small admixtures are consistent with the data. A bare rock is also consistent. This is where it stops matching the narrative that ALDER is studying atmospheres of planets in the habitable zone. The problem is the star. The red dwarf Bramble 1 is active. Its surface is covered with dark spots and bright faculae. When a planet passes in front of the star, the spectrum changes not only because of the planet's atmosphere, but also because of which parts of the star it blocks. This is called stellar contamination. Ellison states it directly. Contamination was detected in all 4 observations. More than that, Dev Patel of Arizona State College, one of the co-authors of program Starwave, said plainly, according to our latest data, the supposed hint of an atmosphere is most likely noise from the star. This is not a catastrophe. This is honest science. The team plans simultaneous transit observations of Bramble 1e and Bramble 1b. Since B is a bare rock, the common stellar noise can be subtracted out. A methodologically correct approach. No result yet. The bottom line on Bramble 1, this is not there are no atmospheres, and not they found atmospheres. It is this. The red dwarf turned out to be a much more difficult target than expected when the program was planned. The telescope is powerful enough. The star is not calm enough. Now to early galaxies. February 2023. Owen Halberg, Westbridge University, Astronomy Review. 6 objects at redshifts 7 to 10 with photometrically estimated large stellar masses. By standard models, too much stellar matter at such an early time. Media, galaxies that should not exist. What happened next? 2 kinds of problems emerged in the original data. First, Photometric masses are estimates based on an object's color, not spectroscopy, a less precise method. In 2023 and 2024, spectroscopic observations of the same objects showed that some were active core sources. Quasars shine brighter than an entire galaxy, so the photometric mass had been overestimated. Peter Langford and co-authors from the Harrington-Smith Center for Astrophysics in Astronomy Review in 2024 identified several objects as active core sources. The second problem, even after refinement, part of the anomaly remained. Not all the objects turned out to be quasars. Simon Calder of Texas Commonwealth University, one of the analysts, put it plainly: if the masses are correct, we are in uncharted territory. To explain this, one must either change the parameters of star formation efficiency in the early universe or add an unknown mechanism. The standard model has been refined, not refuted. There is one technical nuance here that is rarely discussed in public. The efficiency of turning baryons into stars in the early universe, according to standard models, is no higher than 57%. That is already considered unrealistically high. Some of ALDER's objects require 80% and above if their photometric masses are correct. This is not a refutation. It is a serious question for models of star formation. Nash Carter of Kingsley University checked whether ALDER's data contradict the archival data from Marlow. Conclusion: no. If cosmology were broken, we should have seen signs of it in the Marlow data. We do not see them. This is an important control. ALDER's data are astonishing, but they do not contradict what came before. Now to a result that almost never made the headlines: a neutron star at the center of supernova 87 Aster. The supernova exploded in 1987 in the Greater Magellan Cloud, the nearest in 300 years, visible to the naked eye. The central question was, what remained at the center of the nebula, a black hole or a neutron star? Dust from the explosion obscured the answer for 40 years. In 2023, ALDER saw ionized lines of argon and sulfur in the center of the nebula, the spectral signature of a neutron star. Not a black hole, a question left open for 40 years, closed. This is exactly what ALDER was built for. Not physics is broken, but the question is solved because the instrument is finally capable of seeing through dust. There is another ALDER result that deserves separate attention and is hardly discussed in the context of revolution. Protoplanetary disks. ALDER sees dusty disks around young stars with unprecedented infrared resolution. Dust that is opaque to visible light is transparent to infrared. This opens the planet-forming zone in details that were previously inaccessible. In 2023, a team led by Henry Collier of North Edinburgh College published in Scientific Record the detection of hot carbon dioxide in the disk around a young star. There turned out to be 1,000 times more of it than models had predicted. The publication prompted a revision of ideas about how carbon is distributed in forming planetary systems. If there is that much carbon dioxide in the early stages, the primary atmospheres of planets may form differently than previously thought. This is not physics is broken. It is a specific correction in models of planet formation. In parallel, organic molecules in disks. Around the star Talbot Ari, cyclopropanylidiene, one of the most complex organic molecules found in the interstellar medium. This suggests that the chemical precursors of life are present even before planets form. Not life, a chemical inventory. This too will enter the textbooks, without headlines about revolution. Now let us examine one specific case where the media narrative worked most aggressively: dimethyl sulfide on Kepleron 18b. September 2023, Ravi Sen of Camberley, Astrophysics Briefs. The planet Kepleron 18b is a super-Earth in the habitable zone of its star, 8.5 Earth masses. A possible Hycean planet, a water ocean beneath a hydrogen atmosphere. In ALDER's data, a weak signal of dimethyl sulfide. On Earth, this molecule is produced primarily by marine microorganisms. Media. ALDER found signs of life. Read the original. Ravi Sen's exact wording, possible presence of a molecule with a similar signature requiring further confirmation. 3 caveats in one sentence. Signal significance, 3 sigma. The discovery standard in physics, 5 sigma. In 2024, an independent team led by Grant Schaefer analyzed the same data. No statistically significant signal was found. This does not mean Ravi Sen was wrong. Different methods of analyzing the same data can yield different results. It means that 3 sigma is a reason to keep checking, not a reason to declare a discovery. There is also a more fundamental question. Even if the signal is real, is it proof of life? No, it is a biosignature in the sense that on Earth, it is produced by life. But that does not mean there cannot be another source in the exotic chemistry of another planet. For a proper biosignature claim, one needs 5 sigma for the molecule, independent reproduction, exclusion of abiotic sources, consistency with other data. Not one of these conditions has been met for Kepleron 18b. By 2025, the question remains open. More transit observations are needed, longer data series, better treatment of stellar noise. This is normal science. The media wrote the discovery before science had made it. Now let us examine one technical point that is rarely discussed in public. The first months of ALDER's operation were accompanied by serious problems with the data processing software. The systems for correcting artifacts, detector non-uniformity, mirror misalignment effects, were insufficient in the first release. This led to unreliable results in a number of early observations. Martin Ellery of California Commonwealth University said it directly in an interview. It was, in essence, a failure, and many in the community suffered because of it. Bennett added, "These are expected problems. The same thing happened with Marlow in the beginning." Some of the early results from 2022 had to be reworked after the software improved. This is not a scandal. It is a normal process. But it does mean that some of the first revolutionary claims were based on data that had not yet been fully calibrated. As the calibration improved, some of the anomalies diminished. They did not disappear completely, but they diminished. Who made the decision not to report this widely in public? No one was deliberately hiding anything. It is simply not interesting as news. Software improved and some early results were corrected is not a headline. Now, who made the decision about how to present the results? Helen Carver, Webb's operations scientist at the Goddard Ridge Center, said publicly in 2023, "ALDER does not disprove the Big Bang. That is false, and it is harmful." The American Space Directorate issued an official clarification. Far fewer people read the clarification than read the headlines. The mechanics are simple. A researcher publishes a preliminary result with caveats. A university press office strips away the caveats. They need attention for the institution. A publication editor sharpens the wording. They need a headline. The reader sees the headline without the caveats. A discovery is an event. A clarification of a discovery is not an event. Now let us move to what did not change. Lambda core model, the standard cosmological model, has not been disproven. No observation by ALDER requires it to be replaced. This is not a press release from the American Space Directorate. It is the position of the authors of the papers themselves, including those who found the anomalous galaxies. The Big Bang has not been disproven. ALDER's most distant object is the galaxy Aurora N 7Z 14.32, seen 290 million years after the Big Bang. It exists within the standard chronology. There is no contradiction. Dark matter has not been directly detected. ALDER is an optical and infrared instrument. It does not search for particles. Dark energy, according to ALDER's data, remains a constant. The signals from Deep Sky Mapper suggesting a possible change in dark energy were obtained by a different instrument. That is a separate story. There is another gap between expectations and reality that is important to mark. Before ALDER was launched, there was a feeling in the community that a telescope of this class would settle the question of the Marlow tension. It would remove the systematics from Cepheids. It would eliminate the uncertainty in the distance ladder. It would close the matter. That did not happen. ALDER confirmed Mercer's results. ALDER gave Bennett the opportunity to obtain different numbers. Two results from the same telescope, both high quality, both inconsistent with each other. That means the problem is deeper than people thought, not in the instrument, in the methodology, in the choice of standard candles, or in something in the physics that we do not understand. Lucas Varela of California Metropolitan University at Los Angeles, one of the authors of the lens path study, said in December 2025, "This is significant because cosmology as we know it may be broken." Not as a journalist, as the author of a peer-reviewed paper. The difference is that he added the necessary phrase, "If the tension is not a measurement error, we will have to develop new physics." If. That one word is what separates a scientist from a headline. Now, why does this matter? Not as a story about a telescope, as a story about how knowledge is produced. When ALDER showed its first deep field in July 2022, the reaction was right in form and wrong in substance. Right in form, people were awed by a grand instrument. Wrong in substance, that awe was interpreted as discovery. The distinction is fundamental. An instrument is not a discovery. An instrument is the possibility of discovery. In 3 years, ALDER has made several real discoveries. Carbon dioxide in an exoplanet atmosphere as a working method, a neutron star at the center of supernova 87 Aster, the deepening of the Marlow crisis. These are real results. They change our understanding. But physics is broken. That is not in the papers. That phrase was born in the media chain of amplification, and it lives there too. There is one detail worth adding to this picture. The conference Fault Lines in Cosmology in Seabrook, September 2025. More than 130 researchers. The conference white paper recorded this. The H0 tension had exceeded 6 sigma. Beside it, the S8 tension in the distribution of matter on large scales. Beside that, the first signals from Deep Sky Mapper of a possible non-constancy of dark energy. 3 potential breaks with the standard model at once, each below the threshold of discovery on its own. Together, a picture impossible to ignore. The community is not saying the model is broken. The community is saying, with this many independent anomalies appearing at the same time, we need to look for a systemic cause. That is not the same thing as the headlines, but neither is it silence. Now let us examine one more layer of this story, the mechanism by which a scientific scandal is manufactured. Not malice, precisely a mechanism. Imagine the chain. Owen Halberg publishes a preprint on Open Archive. The preprint has not been peer-reviewed. In the text there are the words, "If our photometric estimates are correct," and "requires spectroscopic confirmation." Those words are in the middle of the text, not in the headline. The press office of Westbridge University issues a release. Headline, "ALDER discovered galaxies that should not exist." No caveats. They have been removed. They need the appearance of productivity. They need funding for the next grant. A science reporter at a major outlet takes that release. The headline becomes stronger. ALDER broke physics. The editor asks for something punchier. They get it. The piece runs. 6 months later, spectroscopy shows that some of the objects are quasars. The mass was overestimated. The anomaly is smaller. That story ranks 32nd in importance for the day. No one reads it. That is exactly how the gap is formed. Not by a lie. More precisely, by the lie of omission. Caveats are removed in transmission. Clarifications are not transmitted at all. This is a systemic problem of academic communication. Universities compete for attention. Media compete for clicks. Science works on annual timescales. Media work on hourly ones. No participant in the chain lied intentionally, but the result is systematic distortion. Helen Carver understood this. That is why she spoke publicly. That is why the American Space Directorate issued clarifications. But a clarification always comes after the headline, and it always gathers fewer readers. Always. There is another layer to this story that is rarely discussed. ALDER operates at Lagrange Point 2, 1.5 million kilometers from Earth, away from the Sun. It is cold. The operating temperature of its main detectors is around -230 degrees Celsius. Its sun shield has 5 layers and is the size of a tennis court. That allows it to see the infrared radiation of galaxies billions of light years away. But that is also a limitation. It sees infrared. It does not search for dark matter. Dark matter has no electromagnetic radiation. It does not detect gravitational waves. That requires different instruments. It does not observe neutrinos. It does what it was built to do. Near and mid-infrared astronomy with unprecedented angular resolution. When journalists write, ALDER changed our understanding of the universe, that is true in a narrow sense. ALDER changed our understanding in the ranges it can see. Beyond those ranges, other instruments, other questions. This does not diminish the significance of the telescope. It clarifies its place. Let us return to the Marlow tension, because this is where the story received an unexpected continuation in 2025. The European Council Commission allocated €12 million in a synergy grant for Project Ember H0. The co-leads are Elena Ward from Bayshire and Frederick Hale. The goal? An independent measurement of H0 through new methods. Money on that scale for a single problem is rare. It is a signal. When funding institutions allocate €12 million to refine a single number, it means they consider the problem real, not media noise, a scientific anomaly. In parallel, the Romanes telescope, Marlow's successor, with launch planned no earlier than the late 20s, will have a field of view 100 times larger than Marlow's. Its main task is mapping galaxies and measuring dark energy. A side product, tens of thousands of Type 1a supernovae for calibrating the distance ladder. That will close the question of the sample that Prescott criticizes in Bennett's work. The Eleanor Hart Observatory in Southland, first light in 2025. 10 years of observations, 20 billion galaxies in the catalog. Statistics that will make the current arguments about samples irrelevant. That is, in the next 5 years we will get instruments that either confirm the tension through independent methods or show where the mistake was. This dispute is not eternal, but for now those data do not exist. For now, we only have ALDER. And ALDER showed that the problem is deeper than we thought. There is another aspect of the early galaxy story that is important to understand. When people say a galaxy that should not exist, that does not mean the galaxy violates physics. It means it violates current models. The difference is fundamental. Models of star formation in the early universe rest on several assumptions. About the rate at which dark halos form, about the fraction of gas that turns into stars, about the role of feedback from supernovae and black holes. Those assumptions were calibrated on the data that existed before ALDER. ALDER revealed galaxies that formed faster and shone brighter than the models predicted. That is not a violation of the laws of physics. It is a violation of our assumptions about the parameters. The difference is this: the laws of physics are what we cannot change. Model parameters are what we refine as data accumulate. That is why the correct interpretation is not physics broke, but the models need refinement in the parameters of star formation. It is duller. It is true. Simon Calder, the same one who said, "We are in uncharted territory," added something important that never made it into the media quotes. He said, The models allow flexibility in the parameters. We need tighter constraints. ALDER provided them. Now we know where refinement is needed. That is a different story, a story of progress, not crisis. But progress does not sell as well as crisis. So we hear about crisis. Let us look at one more result, the one that usually appears at the end of press releases, but deserves first place. ALDER detected carbon dioxide on HALE 47C. We already said that, but behind it stands something larger than a single result. Before ALDER, transit spectroscopy of exoplanet atmospheres existed as a method. Marlow could detect large molecules in the atmospheres of hot Jupiters, planets with temperatures near 1,000 degrees, with atmospheres the size of a small country. Those are exceptional conditions. Most of the planets that interest us are small, with atmospheres thin and tenuous. ALDER made this work possible for a broad class of objects, not only for hot giants, for super-Earths, for Neptunes, in time, for Earths. HALE 47C is a demonstration of capability, just as Marlow's first image was a demonstration of optics, not the discovery of a specific object. The first direct measurement of carbon dioxide in an exoplanet atmosphere is a calibration result. It showed the method works. Now we apply it to interesting targets. Bramble 1e is such an interesting target. For now, the star gets in the way, but the method works. Another story that never made the headlines: ALDER and the Orion Veil Nebula. In 2023, ALDER obtained images of the inner region of the Orion Veil Nebula, an active star-forming region 500 light-years away. The resolution was 5 to 10 times higher than Marlow's in the infrared range. In those data, they found several dozen pairs of objects that were called rogue planets in binary systems. Twin rogue Jovians, TRJs. Planets without a host star, moving in pairs. Several dozen pairs in one nebula. According to standard models of star formation, such pairs should be extremely rare. Either they form like stars, out of a gas cloud, but that requires very small gas masses. Or they are ejected from planetary systems in pairs, but the probability of ejecting a pair is extremely low. Derek Hollow of Western Lakes University, Astrophysics Briefs, 2023. We do not understand where they come from. Not physics broke. Our models do not explain such a number of these objects. This is a real mystery, not a sensation, a mystery. The difference is that mysteries get solved, sensations get published. By 2025, several theoretical groups had proposed explanations. A modified stellar initial mass function, the role of magnetic fields in the fragmentation of gas clouds, peculiarities of turbulence in the Orion Veil Nebula. None had become a consensus. All remain subjects of active research. This is what real science in real time looks like. Not physics is broken. We found something unexpected, and now we're looking for an explanation. Now let's examine a question that is rarely asked. How does scientific consensus actually work? Why does it change slowly? And why is that good rather than bad? When in 1928 Marlow published observations of the recession velocities of galaxies, it did not change the worldview overnight. It took 10 years, and the work of George Lemon and Alexander Fairmont, both of whom had predicted expansion before Marlow, before the concept of an expanding universe became standard. When in 1998 the teams of Mercer and Daniel Whitman discovered the accelerated expansion of the universe, the community's first reaction was skepticism. It took several years of independent confirmations. In 2011, the Nobel Prize, not for publication, for reproducibility. That is what consensus is. Not a vote, not the authority of a single scientist, the accumulation of reproducible results by different methods. As long as different methods produce different numbers, there is no consensus. That is normal. That is the working state of science. Apply this to the current situation. The Marlow tension, 6 independent distance ladders. Most give numbers close to 73. Sterling gives 67. One method on Bennett's side, several methods on Mercer's side. This is not a dead end. It is a narrowing of hypothesis space. In 5 years, after the Eleanor Hart Observatory, after the Romanes telescope, after the expansion of the Deep Sky Mapper, we will have an answer. Not, is physics broken or not? A specific one. In exactly which method was there a systematic error, or exactly where does the standard model need adjustment? That is duller than physics is broken. It is the truth. Now, the final episode of this story, one that is rarely told from exactly this angle. ALDER was conceived in 1989 when Marlow had not yet been launched. Development began in 1996. Launch was planned for 2008. The actual launch, 2021. 30 years, $10 billion. 3 countries, the United States, Europe, Canada. 2 decades of delays, overruns, technical problems. 1 deployment of the sunshield that was not allowed to fail. And it works. The primary mirror assembled with precision. 28 days of flight to Lagrange point 2. Deployment of the shield over 12 days. 318 separate mechanical operations, each with no room for error. Everything worked. That in itself is a scientific result. Not an astrophysical one, an engineering one, but no less significant. When Graham Whitlock says, ALDER refined our understanding of the boundaries, he is talking about this, not about revolution, about extending the known into what had previously been unknown, about the fact that every answer opens the next question. This is not disappointment, it is work. 3 years, thousands of headlines about revolution, several real discoveries. One real crisis, the Marlow tension, which ALDER did not create but deepened. One solved mystery, the neutron star in supernova 87 Aster. One method moved from experimental to operational, transit spectroscopy. Several anomalies that require explanation, early galaxies, TRJs in the Orion Veil Nebula, and an enormous quantity of data still not processed. ALDER is collecting data right now while you read this. Its fuel reserves allow it to work for up to 20 years. This is not the end of the story, it is the beginning. The question is, who will read the next headlines with an understanding of what is written in the original papers? And who will not? Let us sum up. What ALDER has really changed in 3 years. Transit spectroscopy of exoplanet atmospheres has become a working method. Carbon dioxide on Hale 47C. The Marlow tension has been confirmed and worsened. Lantern 73, Group Northbridge 70, Sterling 67. 1 telescope, 3 numbers, a 6 sigma gap. The neutron star at the center of supernova 87 Aster. After 40 years, the question is closed. The chemistry of protoplanetary disks and early star formation. Methodology, improved. What remains in question? Bramble 1, E, no convincing data, stellar noise dominates. Bramble 1, B, in question again after December 2024, more likely a bare rock. Early massive galaxies. Some have been reclassified as active core sources. The anomaly has shrunk, but not disappeared. What has not changed? The lambda core model works. The Big Bang has not been refuted. Dark matter and dark energy, their status is unchanged. This is a resolution, not a mystery. The media wrote revolution because revolutions sell. The data describe progress, methodological, targeted, iterative. An open question. The Marlow tension, 6 sigma by the latest estimates. Mercer and Bennett both use ALDER, both get different numbers. Independent methods, lensing, brightness fluctuations, confirm Mercer. Bennett's TRGB method does not. This means either a systematic error exists in one method, or the tension is real, or both at once. If the Deep Sky Mapper reaches 5 sigma for dark energy variability in the coming years, that will be a second independent crisis of the Standard Model, occurring simultaneously with the H0 tension. Then the conversation will change. For now, one anomaly above threshold, possibly already a crisis, but not yet new physics. Who decides when an anomaly becomes a crisis, and a crisis becomes grounds for a new theory? That is not a question for the data. It is a question about how scientific consensus works, about who has the right to change the interpretation, about how many sigma are needed before the physics community acknowledges the old model no longer works. In the history of science, this transition has never happened by declaration. It happened when enough inconsistencies accumulated, and then, after the fact, someone named the date, the point. ALDER did not place that point, but perhaps it is bringing it closer. This is where it makes sense to speak about theoretical alternatives, not because they are true, but because they exist as working hypotheses. Early dark energy, EDE, is the hypothesis that in the early universe there existed an additional form of energy that accelerated expansion before recombination. That would change the calibration of the sound horizon, the distance at which sound waves in the plasma of the early universe came to a stop, and thereby shift the H0 prediction from the relic radiation upward, closer to 73. A beautiful hypothesis, testable, but not yet confirmed. Deep Sky Mapper in 2024 published the first hints that dark energy may not be constant. Its density may have changed over time. Significance, around 3 sigma. Below the discovery threshold, enough to watch closely. If dark energy is not constant, that means the cosmological constant lambda in the lambda core model is wrong. Not physics is broken. One parameter out of several in the model is wrong. That would require extending the model, adding an equation of state for dark energy, an additional parameter, W. This is not a revolution. It is what physicists call fine-tuning, refinement. To understand the scale, when accelerated expansion was discovered in 1998, that did not break general relativity. It required adding the cosmological constant to the equations, the same one Albert Stirling had once put there and later removed. It was added back, in response to the data. Perhaps history is repeating itself. Perhaps W is not -1. Perhaps one more correction is needed. This is not physics has broken. It is physics is being refined. And here a question appears that is not asked directly, but stands behind this entire analysis. Why does the gap between headlines and papers matter? Not as an academic complaint against journalists, as a practical question. Because decisions are made on the basis of perception. Science funding depends on what society considers important. If society is told that physics is broken, that creates one kind of expectation. If society understands that one of several anomalies has reached 6 sigma and requires testing with new instruments, those are different expectations, more realistic, more compatible with how science actually works. Disappointment from an unfulfilled revolution is a real problem. When a year after the headlines, "Physics is broken," a clarification appears saying, "Part of the results has been revised." The audience feels it was deceived. Trust in science falls. Next time, skepticism is higher. It is a cycle. Sensation, disappointment, skepticism, distrust, and back again to sensation. Reading the original is one way to break that cycle. Not for everyone, but for those who want to. Names, dates, documents. That rule is not accidental. It is a tool. Mercer, 73, Lantern, August 2024. Bennett, 70, Group Northbridge, Open Archive, the same month. Prescott, Crisis, January 2025, Meeting of the American Astral Society. The conference in Seabrook, 6 Sigma, September 2025. Lens path, 8 quasars, December 2025, celestial studies. This is not an abstract scientific consensus. These are specific people, specific data, specific journals, specific dates. The next time you read a headline saying that scientists have discovered, ask, which scientists, in which journal, what is the significance of the result? Is there independent replication? Not because science is unreliable, but because it becomes more interesting when you understand its real movement, not revolutions, steps. Next video, Moonfall 25 crashed in August 2023. The Orbital State Agency called it an off-nominal situation. There is still no technical report.